Hello and welcome to this video. My name is Ssonko Julian. I'm a member of Group CS2 which has Senkungu Shawn, Okello Arnold, and Rusezeera Michael, supervised by Mr. Ggaliwango Marvin. Our title is Federated Dermatology Screening with vision language models for skincare recommendations in Uganda. And our keywords are federated feature learning, large vision models, dermatology screening, knowledge distillation, graph-based reasoning, and health digital markets. So in our background, we highlight a crisis in Uganda, a dermatological crisis that is represented by the existence of approximately 25 specialists and a prevalence rate for skin diseases at 30 to 70% for the population of developing countries like Uganda. This has led to geographical isolation and financial limitations that continue to restrict access to dermatological care in rural areas, that has led people to resort to informal sources of information as well as guidance from social media that leads to misdiagnosis and problematic treatment of skin diseases. So with that introduction, I go and talk about our keywords. Our first keyword is federated learning, which involves a global AI model on a server and then local AI models deployed on devices. These models learn, train, make predictions, and based on their predictions and the actual truth, they update the server with their weights. Then federated feature learning takes a step to make sure they exchange learned features rather than just hard model weights. So we talk about large vision models. Large vision models are a type of model that involve dual encoders, which is the text encoder and the image encoder. These both go for attention, and different models have different architectures, but it generally involves an image encoder, a text encoder, the attention step, and the output being maybe a textual description of what's happening, classification results, and a matrix or a vector describing the confidence with which the model has made a prediction. We have knowledge distillation, which involves reducing model size to make sure that we have a teacher model that is larger than a student model. The student model learns from the teacher model. The teacher model is pre-trained, gives soft labels to the student model, which also receives hard labels from the dataset, so that the student model can then be deployed on other smaller devices that can run it without being computationally intensive while not losing accuracy or data. We have graph-based reasoning. It's a process that involves analyzing data, analyzing relationships between that data and the different data points or sources in your dataset. So you query, get a response, get analysis, go through the different paths, and then the different paths give you the different connections between the data points. We have dermatological screening, which involves use of optical tools, eye test, or computer tools to analyze skin lesions and see where dermatological issues could come from, identify diseases, and classify conditions that can then be used for a diagnosis. We have related works here. A couple of papers involved. We have around 6 papers here and more in the 4 papers here and more in the access document. The first paper we talk about here involved an LLM, rather a visual encoder with learnable linear projection, and then an LLM used for inverse graphics, basically getting an image and producing the graphical representation of that image in 3D. The limitation they had here was that the model size was large and training difficulty existed without labeled data. We have the clip model. Clip basically is a dual encoder language model with an image encoder and a text encoder that then provide tokens that go for attention, which is the architecture described here. It uses contrastive learning to align visual and textual representations via dot product similarity. The issue that Clip faced is that it struggles with abstract and systematic tasks and then has poor generalization of out-of-distribution data, an issue that we'll talk about later in the video, as well as sensitive to prompt wording, and inherits biases from web script training data, which is why it can directly be applied to dermatological screening, especially on African skin. We have Viper, which has a frozen vision language model and a reasoning model and LLM. It suffered hallucination from the VLM, and also it is computationally intensive while struggling with complex tasks that involve manipulation of multiple objects. We have PFED LVM, which is a large vision model for latent feature-based personalized federated learning framework in autonomous driving. This is basically using a large vision model with a federated feature learning to allow autonomous cars to learn, update their global server using federated learning and federated feature learning to then train better models, as well as have personalized learning on different vehicle models. The issue is it faced that accuracy was highly dependent on data quality, and that the scalability to handle large amounts of data was not very easy. The large amounts of federated data coming in from the different automated vehicles, as talked about in the paper, was hard to scale with. So that has been the introduction and the literature review. My name is Ssonko Julian. My group mate will take you through the problem statements, and then the video shall go on with the format that we have set. Thank you.
My name is Senkungu Shawn. I'm going to go through the problem statements and the research objectives. So the main application problem, a shortage of accessible, fair, and privacy-preserving dermatology screening tools in low-resource settings like Uganda. We have an estimated less than 25 certified dermatology experts in the country that has over 45 million people. So and the models are needed, and yet they're not very good. So there's a domain for this. Computational problem. Multi-class skin lesion classification under data scarce and heterogeneous imaging conditions. So the data sets are just not there. We have very few data sets for local skin. Most of them are white, Caucasian skins. All the skin diseases, how they affect the black skin, are very few, and they're usually very low quality. under heterogeneous imaging conditions, diverse conditions, poor lighting, terrible angles, the model should still be able to correctly diagnose a given skin disease, so that's what we want to do. We want to have a model that can diagnose a disease correctly. Integration of bias mitigated, privacy preserving diagnostic AI. You don't want people generally don't want to submit their personal data to a centralized server. So what we want to do here instead is to use federated learning, so that you have the models trained locally on your data, on your phone, on your device, and they only send the updates. They don't send your personal image. They don't send so and so has such and such a disease. Only the updates, and then you get the average, the federated weight for the average of those updates, and you update and you train the model. Mobile optimization that would prevent you from sending people's data. So mobile optimization for low resource settings. These large vision models are very resource intensive, yet we have generally low end devices. So you want to optimize for lower end resources. So this one now we use knowledge distillation, so that it offsets the intensive part, the diagnosis, the classification, and you have a lightweight model that's on the device that's optimized for low end devices. So the research questions and objectives, generally you want to create a robust model that maintains privacy and works in low end devices. So the objectives come to highlight each of those. So one is to create and augment a distributed dermatology data set representative of local skin conditions, to basically have a high quality data set that has black skin. To carry out feature extraction and engineering. This is the whole point of the model, so that you can have the disease diagnosed correctly with very good accuracy. To train and evaluate models in a federated learning environment for skincare recommendations. The whole thing, you want to train and evaluate the model. To deploy an optimal and trustworthy federated learning architecture. This is the same thing. This is the privacy part. You don't want to leak people's the medical sector is very, very strict with how you handle people's data. So the federated learning part, you won't send people's data, you only send the updates. To implement federated feature learning and enabling collaborative training while preserving data privacy. It's a side effect of using federated learning. You preserve people's data set and people's privacy, and you can easily collaborate because people send different training data from their local devices. So the research contributions, the outcomes of this is a decentralized data set creation and curation. Basically, I have the data set I was talking about, feature extraction and engineering, federated training and evaluation for skincare recommendations, and deployment of a trustworthy federated learning architecture.
My name is Rusezeera Michael, and I'm meeting you through the methodology and system architecture and the EDA phase group. So the methodology starts with the training phase, whereby the main large vision model is distributed to different clients, and also an instance is made where we use the actual dominant dataset, which is our main dataset. So each client will run a version of this model on their own dataset. Let's say each skincare clinic would train this model using data from the database of the clinic, and then the different weighted aggregates are then got and sent back to the central server, which has the main LVM, and they will basically. The central server will then use these weighted aggregates, get the average, and update the LVM to make it smarter and more stable, and also increases knowledge in general visual representations, then making it a good teacher model. Then this knowledge is distilled onto a student LVM, which is on a smaller edge device with limited resources, but it will still have high accuracy because the knowledge is distilled from the main teacher model that we fine-tuned using the different aggregates from the different clients. So basically how this will work will be you input an image or upload an image, and then two things will happen with the student LVM. It will run its diagnostics and to generate probability vector and also a feature map, which the feature map will, with the help of the GradCam, will be able to highlight the key areas that we focused on to say you have this issue, like the main area, let's say the original image and then the area focused on. Like this is where the issue is. Then the probability vectors will go to the graph attention network and the knowledge graph to better interpret what the diagnosis is and get a more stable diagnosis, because the probability vector will just be something like 0.6% chance that it's eczema or 0.3% chance that it's ring-worm. So, but the representation network and knowledge graph will be able to narrow this down and give a better context of this, which will be sent to the LLM, and the LLM will then improve this by using natural language processing and give actual diagnosis and recommendation to the user in a more readable way and more understandable way to the user, along with a breadcrumb image for the benign regions that we focused on to come up with this diagnosis. Yeah, that's our architecture. Then this is what I've explained. These are the basically the steps. Then the dataset description and EDA was basically the dataset was sourced from DAMNet Cargo repository. It has about 23 disease classes, and as you can see, there's a big class imbalance, and there's also red channel bias and bimodal image sizes, which are where these images basically represent. So to address the class imbalance, we'll use graph attention networks and diffusion-based augmentation, along with weighted sampling to address the class imbalance, and we'll also use federated learning to ensure privacy by sharing only the model embeddings and not actual images. We won't use the actual data from actual patients, but we'll just get the embeddings on the trained models using those data, on how the model was trained using those data sets, and those will be used to update the main LVM. As you can see here, these images show the general class imbalance. Some diseases like the psoriasis has way more images than smaller diseases, let's say like hair loss photos, alopecia, all that. And also in the aspect ratio here of distribution, we see that most images are actually wider than they are longer in height. Yeah.
My name is Arnold, and I'm going to be taking you through the rest of our presentation. So we trained a couple of models. To start with, we started with the 22.5 a pre-trained model. So this basically takes in an image through the vision encoder to give us a token. So it takes in a couple of images to give us different tokens, which are then passed through the 22.5, which are then passed through the 22.5 decoder, which has medically learned data to give us a prediction. Then we also trained Clip. Clip is a contrastive learning image pre-trained model that takes in image and texture input. So the image is passed through the visual encoder here to give us texture embeddings. Then the text is passed through the text encoder to give us text embeddings. So the model uses cosine similarity. It combines both the texture embeddings and the image embeddings by using the cosine similarity to give us a prediction of the most likely outcome of the disease. Then we also trained Florence Florence, and this is its architecture. And as you can see, it's more of an iterative format. It also accepts both. The image and the texture data, and it learns more of this through search and encoding process. So we also trained the lava model, which is also kind of similar to the clip model. So this takes in an image to give us, it takes in the image and its text. So it takes in the image to give us an image vector, together with a texture. It also converts the text to give us its vector, and then passes this through the model to give us, and that is how the model is trained. So that it gives us a prediction of what could be the most likely outcome of the disease. Then these are the results. These are the results we obtained. These are the results we obtained from training all those different models. And as you can see, for Queen it was 0.42, and Clip was 0.45, and Clip with Focollos. Now, Clip with Focollos focuses more on it doesn't use contrastive loss to train, but rather uses Focollos to train. So that's why we saw an improvement in our accuracy, and this is why we chose the Clip with Focollos. Then we also trained Florence and Lava, and these are the results we got from all those different trainings. And the limitations we had because of these large, due to when you're working with transformers and visual models, basically they were very large models, so it was very difficult when it came to training. Then the annotation of datasets for segmentation. This is basically training the model in such a way that it can get training the model such that it can understand each individual pixel, so that it can learn specific details about the image. So that we had a difficulty with that, which is also a difficulty up to now. Then also low model generalizability on small dataset segments. So the model will learn very well with a small dataset, but if you give it more data, which is still similar to that, training will be the prediction will also be kind of difficult. So the next feature, we want to focus more on deployment of a smaller, robust, and resource-friendly open source model for field dermatology. and that is what we aim to focus on. Then I'd like to thank Mr. Ggaliwango and all the authors of the technical papers we cited, and including the platforms like Cargo Collab and Hugging Face that we use to run these models due to our lack of resources. And these are some of the works we used. Thank you very much.